Okay, so we're going to learn how to go ahead and figure out the pH of a weak acid solution. So this one is a weak acid. Okay, and we're going to figure out how to come up with the pH of this weak acid. And of course, in order to get a pH, what we need is pH is equal to the negative log of the hydrogen concentration, as we learned from the last worksheet. So what we need to get here is, well, we need the hydrogen concentration. If you have the hydrogen concentration, you can then go ahead and get the pH. Okay, so I'm going to show you the real quick way of doing it, the super shortcut, and then I'll show you where we get that shortcut from, so you know kind of where it's coming. If you use the shortcut, that's fine, but we want to know where that is coming from. Okay, all right. So the shortcut here is this: a couple things you need. You need the concentration of your acid. And even though the identity acid is always helpful, the important thing is knowing the Ka. So between the Ka and the concentration, that's all you need in order to figure out your hydrogen concentration. This is the hydrogen concentration at equilibrium right here. Okay, so that's what we're going to need, right? The real shortcut way of doing it is the following. Okay, the hydrogen concentration at equilibrium. Whoops. Let me go ahead. Go back to pencil here. The hydrogen concentration at equilibrium is equal to the square root of the original acid concentration, right? The beginning acid concentration, that 1.0 that we have over here, at times the Ka. Okay. So in this case right here, what you're going to find is that this is 1.0 molar acetic acid with a Ka of 1.8 times 10 minus 5. So what we're going to do is we're going to get the concentration by going 1.0 molar times 1.8 times 10 to the minus 5. Okay, and that's going to equal to, we're going to need the square root. So if I go ahead and plug in, let's go ahead and plug that into the calculator over here. All right, so the square root of 1.8 times 10 to the negative fifth. All right, if I hit equal, it gives me 0.00424, or 424 times 10 to the minus 3. 424 times 10 to the minus 3. Let's go back and go ahead and put that in. 4.24 times 10 to the minus 3 molar. Okay, and then once you have the hydrogen concentration there, right, and that's at equilibrium concentration, you go ahead and plug that into your formula for pH. Negative log of 4.24 times 10 to the minus 3 is going to be equal to, well, let's go ahead and plug that in. All right, back over here. 4.24 times 3. What's the log? Log of 4.24 times 10 to the minus 3. That's going to give me 2.37, or negative 2.37 right here. All right, so our answer then is going to be the negative of negative 2.37, right? Or 2.37. 2.37. Okay, and there's your answer. See how quick that was? So once again, what you did is you took the initial concentration right here, go ahead, right there, took the initial concentration, which was 1.0, multiplied it by the Ka. I should put that as Ka. Or A stands for the acid constant. And here that was, there's your Ka. That was 1.8 times 10 minus 5. All right, and then multiply them together, took the square root, and you ended up with then your concentration right here. Okay, that's your hydrogen concentration, which then you plug into your pH formula right there. and you end up with your pH over here. Okay. So that's how you do it really quickly for a weak acid. Now, where did all that come from? Let me go ahead and show you where all that came from. And once again, that's kind of a shortcut to it, because if you don't remember if you remember that formula up there, then what you can do is you can do a whole ice table, and that's where it came from. It came from an ice table. Right. So the first thing you got to do in order to be able to do these weak acid problems is write the equation for the acid. So aqueous, whatever this acid is. Oh, in this case, I guess it was acetic acid. Let me go ahead and write out the formula for acetic acid. Okay, and that dissociates into H plus, aqueous, and acetate ion, also aqueous. All right, and we're going to make the ice table below it. Okay, and we said we start off with 1.0 moles per liter of C2 of acetic acid, 0 hydrogen, 0 C2H3O2. Now, just a little note. This right here is really not a zero. It's really not zero. If you're putting it in water, actually, there's 10 to the negative 7 moles per liter of hydrogen to begin with. As we saw from water, water starts off with 10 to the negative 7 moles of hydrogen and 10 to the negative 7 molar hydroxide. Okay, so we have that there, but that number is so small that usually gets squashed by whatever we end up putting in there, right? So we're going to assume that that's a 0. Okay, it's a good assumption. Doesn't always work, but it's a good assumption. All right, now that we have our ice table going, we know that some of the acid is going to turn into is going to dissociate. So X moles per liter of the 1 mole per liter is going to dissociate. We don't know how much. But for every mole per liter of acetic acid dissociates, we're going to get S moles per liter of H plus and X moles per liter of the acetate ion. So that at equilibrium, we end up with 1.0 minus X times X times X here. Right, so 1.0 moles per 1.0 minus X moles per liter of acetic acid, X moles per liter of H plus, and X moles per liter of C2H3O2. Okay, so we've got our ice table there, and then we can go ahead and write a equilibrium expression for this reaction. Right, we have H plus and C2H3O2 minus as products. So we're going to use Ka. This is our acid constant, and we're going to go ahead and put the products on numerator. H plus concentration times C2H3O2 minus concentration all over acetic acid. Okay. And whatever acid you're using, you just put the formulas there. They basically all kind of have the same pattern. And what we're going to do here is then go ahead and put, this is the hydrogen ion concentration right here. So we're going to put that in here for equilibrium. This is the acetate ion concentration. We're going to plug that in here. And the acetic acid concentration, this one right here, is going to go down here. Okay, so we'll plug those in, and we're going to end up with X in the numerator times another X, which is X squared, divided by 1.0 minus X. That's going to equal to the Ka. And we saw earlier that the Ka is 1.8 times 10 to the minus 5, right over here. So we're going to plug that in over here. Okay. So 1.8 times 10 to the minus 5. All right, so now we have our equation, all in terms of with just one variable in it, X. So let's solve for it. Now, if you look at this equation, you're going to see that in order to solve for this, you're going to have to go ahead and take the denominator over here. Right, so this denominator over here, and multiply it to both sides. So it ends up over here and multiplying by 1.8 times 10 minus 5, which means you're going to have an x squared term, an x term, and then your constant terms. So you can go ahead and do that, and you can go ahead and use the quadratic formula to solve for that. But I'm going to show you a shortcut here where you can kind of get away from not having to use the quadratic formula. The key here is getting rid of this little x, because this x right here, that one right there, is the one that gives you an x term, and it makes you use the quadratic formula. Okay. So what we're going to do is the following. See how this number is so small? In order for this number to be so small, the numerator has to be much smaller than the denominator here. So what we're going to do is we're going to go ahead and make an assumption and assume that x is a very small number. So much so that 1.0 minus x is about equal to 1.0, because x is so small that, like, if we actually subtracted 1 minus x and rounded, we'd get 1.0 back again. So that's the assumption we're going to make, and it's a good assumption, and we can test it in a little bit. Okay, so let me go ahead and get rid of these things here. All right, so what we're going to do then basically is go, okay, I'm going to assume that x is small, and so 1 minus x is about equal to x, so I can go ahead and ignore that. Okay, and when you do that, now what you've got is x squared over 1 times 1.8 times 10 minus 5. Okay, and so let's go ahead and do that. X squared over 1.0 is equal to 1.8 times 10 minus 5. Okay, redo that 5 here. Okay, which means that we're going to multiply both sides by 1.0 and multiply one part of the side, multiply by 1.0 on this side so that it cancels. And when they cancel, let's go ahead and get rid of them because they cancel, which leaves just x squared on the left side. And what we want to do is just solve for x. So take the square root of both sides. And when you do that, now your x is going to equal to the square root of 1.8 times 10 minus 5, which is the same thing we had up before. Right here, remember when we did this before? Over here, we went ahead and took the square root of 1.8 times 10 minus 5 in order to get this, right? Okay, so what we're going to do is we're going to go ahead and if you put it in the calculator again, you get the same answer, but we end up with 4.24 times 10 to the minus 3. Okay, and so that's your x. And remember that the x is the hydrogen ion concentration. If I go back over here to this one, remember here, my x here is my hydrogen ion concentration. All right, so we found the hydrogen ion concentration. Now we can go ahead and find the pH. But since we got the same number for x, we'll plug it into the pH formula. We're going to end up with the same pH. pH, whoops, let me get the right pen here. Our pH is going to be equal to the negative log of 4.24 times 10 to the minus 3. And that's going to end up being, what did we get before? I think I still have that calculation in the calculator. Log of 4.24 times 10 to the minus 3 here is negative 2.37. Take the negative of that, and that's going to give you 2.37. Okay. And there's your pH again. Okay. So the first one here was just basically all the acids react the same way, behave the same way. So really, this is the right way to do it, by making an ice table, solving for x, and then going ahead and doing that. But you'll notice that I gave you this equation right here. And let me go ahead and point it out here. This equation right here that allow you just to plug stuff in. If you forget, then you can go ahead and use the ICE table. But your hydrogen concentration is just the concentration of HA of your acid, right? So in this case, it was this one right here. This was the acetic acid concentration, that 1.0 right over here. Okay, so it was that times the Ka. Okay. Both those things have something to do with the hydrogen concentration. So that's the shortcut right there, real quick. If not, you can go ahead and do it by doing an ICE table. And I think the ICE table is easier to remember. That's why I'm showing you how to do it. Oh, I forgot the equation. How am I going to do this now? Well, make up an ICE table. And that's it. So at this point, that's how you would solve the for the pH and the pH of a weak acid. And you do that by finding the hydrogen ion concentration. All right, then once you have the hydrogen ion concentration, you plug that into your formula for pH there. Okay. Now, at this point, you're probably good to go with the video. You probably don't have to go any further. I'm going to show you, though, how we would have gotten the same answer had we not made this assumption, and how if we had solved for x, we would have got just about the same answer, right? So remember right here, we said, oh, 1.0 minus x is about equal to 1.0. So I probably won't show this in class, but if you want to see, look at it later, you can, right? So let's go back to this part right here. Let's take this. So this is where I'm going to start doing that. Once again, I'm just going to show you that we'll get the same answer. All right, so let's see. It was x squared over 1.0 minus x is equal to 1.8 times 10 to the minus 5, right? All right, so what we're going to do here is we're going to go ahead and get rid of the 1.0 times 10 to the minus 5. Basically get rid of our denominator by multiplying both sides by 1.0 minus x. Multiplying both sides by 1.0 minus x. Okay, so that these guys cancel. Okay. So at this point in time, we're going to be left with x squared equals to, well, now we're going to have to distribute this here and this here. So you're going to end up with 1.8 times 10 to the minus 5 minus 1.8 times 10 to the minus 5 x. Right. So our quadratic equation is going to end up being, because what we're going to do is we're going to have to subtract this from both sides and add this to both sides, times 10 to the minus 5x. So we're going to end up with x squared plus 1.8 times 10 to the minus 5x minus 1.8 times 10 to the minus 5 is going to equal to 0. All right. So when you have the a quadratic equation, and you want to use a quadratic formula, you can define what was your a. Your a is going to be 1 here. That's the coefficient for x squared. B is going to be 1.8 times 10 to the minus 5. Oops. 10 to the minus 5. And C is going to be negative 1.8 times 10 to the minus 5. Okay. And you'll recall the quadratic formula, which was x is going to be equal to negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, oh great, I hadn't used that in a while and I remembered it. I was a little worried about that. All right, and that's going to make this negative 1.8 times 10 to the negative 5 plus minus b squared 1.8 times 10 to the minus 5 squared minus 4 times a is 1 times c. I'm going to have to draw this down here at the bottom. 1.8 times 10 to the minus 5 All right, so that's all together, all over 2a, which would be 2 times 1. Right. And so let's go ahead and do this. Let's first off work on the thing in the square root part. So what we got is, I'm going to go ahead and do it on my calculator here. 1.8 times 10 to the minus 5 squared minus 4 times 1 times this one was giving me, C was negative, right? Negative 1.8 times 10 to the minus 5. Okay, that's all going to be, oh boy, okay, let me do this again here. 0.8 5 squared, okay, plus 4 times 1.8 times 10 to the minus. I had a syntax error earlier. Okay, so everything here in the square root is basically 7.20 times 10 to the minus 5. Then I have to take the square root of that. So I'm going to have negative 1.8 times 10 to the negative 5. Plus or minus square root of 7.20 times 10 to the minus 5 all over 2. Okay, and square root of the determinant there, square root of 7.20 times 10 to the minus 5 is 8.48 times 10 to the minus 3. All right, so I'm going to, since I need an x that's positive, I'm not going to use the negative. I'm not going to use the negative here. I'm just going to use the positive. And I'm going to subtract 1.8 times 10 to the minus 5. Okay. That's going to give me 8.46 times 10 to the minus 3 divided by 2. And I get 4.2. Basically, I get 4.23 times 10 to the minus 3. Okay. And that's my answer here for x. Right? X equals to, work here. X equals to that. Okay, and that's my hydrogen ion concentration, which is not that far from the other one. The other one was 4.24 times 10 to the minus 3. So it might be off at the third spot, but not all that much. So see, we saved ourselves all this work by making the assumption, and we basically got the same number back, right? And remember, all this work we saved because we made the assumption over here. I don't know if you know how happy your math teachers would be saying that was okay, but that 1.0 minus x right here is about equal to 1.0, so we ignored the x. But that we can do that because this number is small, and since x is in the numerator right here, we assume that since this number is really small, the denominator is much bigger than the numerator. The numerator is much smaller in order to get this ratio right here to be that small. So x had to be really small, so small that when you take 1 minus x, it basically comes back to 1.0. And if you go ahead and try that, there you go. 1.0 minus 4.24 times 10 to the minus 3. Okay. That equals to 1 minus 4.24 times 10 to the minus 3. It's going to give you, it gives you 0.996, which if you round back to 2 significant figures here, rounds back up to about 1.0. Okay, so notice how this is here. Okay, this is how you can check. This doesn't always work, but this is how you can check to see if the your assumption is good. Okay, you can always go ahead and whatever we find for x, what you're going to do is check to make sure that X is not more than 5% of your answer. So X over the initial concentration of HA has to be less than 0.05. Right, so right now we found our X of 4.24 times 10 to the minus 3. The initial concentration was 1.0. Do that again, 1.0. So what is this ratio? 4.2 times 10 to the minus 3 divided by 1.0 is basically 0.0042, which is less than 0.05. Okay, so good assumption. Okay. All right, so that's how you solve a weak acid problem.